Okay, in this video, we're going to talk a little bit more about work. So in the previous video, we were looking at a situation where we had a block on a surface and we had these different forces. We had gravity acting down, which I think we called mg. We had the normal force up, of course. We had an applied force to the right. And then we had a friction force backwards, and we were calculating the work done by these different forces. And we noted that sort of the basic skeleton of the work equation is that the work is equal to the force times the distance. But we learned a couple things that about this equation that are a little bit tricky, and that's that first of all, the force only does work if there's a component of the force that is parallel to D. So I might put a little subscript parallel, that those two parallel lines just mean parallel. So what I mean here is this here is the component, that is the component of the force parallel to D, to the distance moved. So for instance, that means that there's no work done by the normal force and there's no work done by gravity because they're entirely perpendicular. And then there was an additional feature, which is that when the force was opposite the direction of motion, which was the case of friction, then the work was negative. So in this case, the work done by the applied force was positive, the work done by friction was negative, and then the work done by gravity and the normal force were both zero. And it's this parallel nature of the force times the distance that I want to go into in a little bit more detail today, and we're going to refine our equation for work. So let's imagine a different scenario. So now I'm going to have a surface again. So here's the surface here, and I want to have a block on that surface just like before, and I'm going to have now an applied force, but now the applied force is actually going to be at an angle. So it's not going to be entirely parallel or perpendicular. In other words, let's imagine that we have this applied force here. I'll make that a little straighter, something like that. Here's this applied force, FA. And I'm going to imagine that that applied force is at an angle here above the horizontal. And we'll call this angle, well, maybe we'll call it 60 degrees. So then, of course, we would have these other forces. We'd have gravity down. We'd have the normal force up. And maybe just for kicks again, we'll have friction backwards. Now, just to remember something that we'd learned previously, remember in this case, the normal force, maybe I'll just put this as kind of an aside, just as a review here. Recall that in this case, the normal force is going to be less than mg. And that's because there's a component of the applied force rather, that's in the vertical direction. In other words, if I were to go ahead now and split the applied force, and this will be relevant to what we're doing today, if I were to split the applied force into components, I could say there's a component of the applied force in this direction. That would be FA times the cosine of 60 degrees. And there'd be a component of the applied force in the vertical direction. That would be FA times the sine of 60 degrees. And I just want to remind you that in the y direction, so in the y direction, we could say that the two up forces, which are the normal force and this FA sine 60, the component of FA in the vertical direction, have to add up to the one down force, that's gravity. In other words, I could say here that Fn plus Fa sine 60 degrees has to equal mg. So that's just a little bit of a reminder. And that may come in handy as you try some problems later. But I want to get back to work. So the question is, maybe I'm going to ignore the other forces since we already know how to deal with the other forces. I'm just going to ask one question, and that question is going to be how much work, or how should we calculate, how to calculate the work done by the applied force. And I'm realizing now as I ask this question, you should be thinking to yourself, well, it's impossible. because I have not given you a distance. All right, we need to know a distance. Let's assume that the distance moved here is, and we'll put some numbers in. Distance is, we'll say 10 meters, try to make life easy. And we'll say that this applied force is, I don't know, we'll say 8 newtons. So how do we calculate the work done just by this applied force? Well, you may see where we're headed here, but I've already split the applied force into two pieces. There's this component, which is perpendicular to the 10 meters. That will do no work. So this does no work because it's perpendicular, and perpendicular forces don't do work. So it's only this force then that's actually going to do work. This one does work. The parallel does work. Does work because it's parallel. So in other words, what I'm going to do is I'm going to say in my work calculation, if we noted before it's F parallel times D, that means that the way I'm going to calculate work here is going to be F times D times the cosine of the angle theta between them. So here theta, the angle between F and D, is 60 degrees. So I'm going to just make a note of that. Theta is the angle between F and D. So in this case, the work done would be equal to the force, which is 8, times the distance, which is 10, and then I'm going to multiply by the cosine of 60 degrees. And the reason, again, that I'm doing cosine of the angle is we can see that that's going to allow me to incorporate the fact that the applied force times the cosine of 60 gives me just the component of the applied force that's parallel to D, that does the work. And so this is going to give me the work value of 40 joules. So this is, just so we're clear here, I plugged in 60 for theta. There we go. So I'm using 60 degrees here. So that would give me a positive 40 joules. So now we have an equation, this equation right here. I'm going to go ahead and put a box around it now because it is now an equation that we can always use right here. Work equals F times D times cosine theta. And here, just remember this note about theta. It is the angle between F and D. So if you remember, if some of you probably know a fair bit about this function, the cosine of theta, but just remember when theta is less than 90 degrees, then the cosine of theta is positive. When theta is more than 90 degrees, the cosine of theta is negative, and when theta equals 90 degrees, the cosine of theta is 0. So this will actually incorporate what we already know. So when the angle is bigger than 90 degrees, that would be in the case of whenever the force is going backwards, any angle bigger than 90 degrees. So if the force were headed in this direction or straight back, the angle is bigger than 90 degrees, you're going to get a negative work value. If it's less than 90 degrees, so if it's this way or that way, you're going to get a positive work value. And then, of course, when it's 90 degrees, you get a 0 work value, so that's consistent. This equation is consistent with what we already learned. So moving forward, you're going to be using this equation, work equals FD cosine theta, for the case when the force is neither entirely parallel nor entirely perpendicular to the direction of motion.